So, hello everyone. I am Riturani Mandal. I am a PhD student in IIT Bangalore. Currently, I am in my second year of PhD, and every Monday from 7 to 8 p.m., I take this class where I solve inorganic chemistry questions which came in GATE. So, currently, we are solving inorganic questions from the year 2021. I am audible?
Yes, ma'am.
Yes, ma'am.
Okay. So, today we will start like Today we will start with question number 12, which came in GATE 2021. So today we will be solving this question number 12, which came in GATE 2021 chemistry paper. So the question is the reaction of, okay, so I mainly solve questions which are from coordination chemistry, organometallics, and main group chemistry. Okay. So here the question is the reaction of NiBr2 with two equivalents of PPS3 in CH2 at minus 78 degrees Celsius gives a red colored diamagnetic complex, which is having the formula NiBr2 PPS3 whole 2. This transforms to a green-colored paramagnetic complex with the same molecular formula at 25 degrees Celsius. The geometry and the number of unpaired electrons in the green-colored complex respectively are. So, uh, wait, somebody join. Okay. So in this question, this thing is given that NiBr2 is reacting with two equivalents of triphenyl phosphine in CH2 and at minus 78 degrees Celsius, this compound is forming NiBr2 PPS3 whole 2, which is red in color, but at 25 degrees Celsius, this compound, like we can see the change of color from red to green. But the compound is having same molecular formula of NiBr2 PPS3 whole 2. So first of all, like in this question, what we have been asked is to find the geometry of the complex and the number of unpaired electrons. Geometry and number of unpaired electrons. Just wait. This problem. Okay. So first of all, here we can see that nickel is having a coordination number of what? Anyone?
Four.
Okay. So what are the possible geometries for for a metal with coordination number 4?
Square planar,
Tetrahedral and square
tetrahedral, and
Okay. So tetrahedral is having hybridization of sp3, whereas square planar has an hybridization of dsp2. Okay. So in this case, uh, anyone oxidation state of nickel? You guys can work
Plus
out.
plus 2.
Plus 2.
Yeah. Yeah. So how plus 2 is coming? If we consider oxidation state of nickel as X, bromine carries a charge of -1 and there are two bromine. So 2 into -1 plus ppS3 is a neutral ligand. So 2 into 0. This is equal to, this is a neutral complex, right? So this is equal to 0.
0.
Yeah. So that's why X is equal to 2. And nickel is having an oxidation state of +2. So generally the electronic configuration of free nickel is 3d8 4s2, right? So when nickel is present in +2 oxidation state, then nickel will have 8 electrons in its d orbital. Okay, so nickel in this complex, nickel is a d8 complex. So these are, like, if this is for the red complex. Okay, so in the question we can see that it is given that the red colored complex is a diamagnetic complex, right? Diamagnetic complex means what?
No
Means,
unpaired electron.
yeah, so in this case all the electrons are paired and we know that we have a total of 8 electrons. Okay, so since there are no unpaired electrons, the way we will fill the d orbital is 1 2 3 4 5 6 7 8. Okay, but since we don't have any unpaired electrons, so it will be present like this. That means 1 2 3 4, right? So in this case this will be vacant. And we have one more orbital. So here how electrons will be filled? First pair of ligand will give an electron here, one in s orbital and the other two in the two p orbitals. That means the hybridization of this complex will be dsp2, right? And dsp2 means what?
Square theta.
Which geometry?
Square theta.
Okay, so this, when we are getting this red color, in that case, NiBr2 PPS3 whole 2 is a square planar complex. Now, at 25 degrees Celsius, what is happening is this complex is changing its color from red to green. So, also here also we can see that in this question only it is given that green colored complex is a paramagnetic complex. That means what? We will have unpaired electron in this case. Okay, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, right? So in this case, it will be like this. Therefore, the ligand will give its electron to 1s and 3p. And we will have a hybridization of sp3, which means what geometry?
Tetrahedral.
Okay, so now we know that what is the geometry of this green colored paramagnetic complex. And also we know the total how many number of unpaired electrons.
2.
Okay, so it is equal to 2. So already we know the answer of this question then, that the correct answer will be tetrahedral and 2, right? But now you guys may have questioned that why this change in color. Anyone can answer that? Why we are seeing this change in color?
DD transition.
Yeah, DD transition, that is fine. But why, like,
Ma'am, due
in
to
both
unpaired
cases, there
electrons.
are DD transition, right?
Ma'am, due to unpaired electrons.
Due to unpaired electrons. See, here also we are having paired number of electrons, but still there is some transition. That's why we are getting this red color. Or else this compound would not have shown any color. So this is because of this thing. See, when we are having, how many d orbitals we have? 5, right? So when it is present, when we are having a free ion or when d orbital is present in a spherical electric field, sorry, spherical crystal field, then all these 5d orbitals are degenerate in energy. But when we are moving to a square planar geometry, then this d orbital splits into four in different four different energy sets. Okay. So the lowest is gxz dyz for square planar. Then comes the dz square, then dxy, and then dx square minus y square. So here what we know is we are having uh, eight electrons, right? So one, two, three, four, and all are paired. Okay? Seven, eight. Okay? And this gap between dxy and dx square minus y square is the crystal field splitting for square planar complexes. Okay? And similarly, when we will when d orbitals will be present in a tetrahedral crystal field, then it splits into two degenerate sets, which are E and T2 set. Okay, so this E set consists of dz square and dx square minus y square, whereas T2 set will have dxy, dyz, and dxz. So here also, then one, two, three, four, five, 6, 7, 8, right? So, and here the crystal field splitting is delta T, right? So, in this case, the transition we are saying is one electron from here will get transited to one of the T2 orbitals. And in this case, we are getting the red color because of the transition of one electron from this HOMO, that is gxy, to dx square minus y square. Okay. So now this crystal field splitting, if we this delta of square planar is similar to the crystal field splitting which is observed in octahedral complexes, whereas this delta T, that is crystal field splitting for tetrahedral, is lower, lesser than that of delta O. It is 4 by 9 times of the octahedral crystal splitting. That means what? Delta SP is, sorry, is greater than delta T, right? So now you guys know that this delta is equal to the change in energy, like the energy required for the transition. And we know that delta E is inversely proportional to lambda observed, like wavelength of the light observed. Okay. So since in this case, in square planar case, the energy gap is more, that means that lower wavelength light will get absorbed, and what we see I think you guys know this, that whatever color is absorbed, we see the complementary color to that. Okay, so low wavelength means we know this with your red is having the maximum or the lowest wavelength. Anyone?
Ma'am, high wavelength.
Okay, so in this case what we are saying is that the lowest wavelength will be observed like somewhere around with like violet or indigo. Okay. So, actually, what happens is, since low wavelength is getting observed, that means we will get the opposite to that. Like higher wavelength, we are that's why observing red. Okay. Whereas in this case, the energy gap is less. That means high wavelength light is getting absorbed, and we are observing a low wavelength color. So in this case, we are getting green as the color. So now you guys know about the color, why it is having two different colors for the same complex. Once when it is in square planar geometry, it is giving a red color, whereas when it is going to a tetrahedral geometry, it is giving green color. Clear?
Yes.
Okay. So this question is clear, I hope. Any doubts? Yeah. Hello. Can I move on to the next question? Am I audible?
Yes, ma'am.
Okay. So I told you this concept about color because sometimes you will get questions like that, that why something is showing a one color whereas a compound with the same molecular formula is showing a different color. So this geometry matters. Okay. Because why geometry matters? Because for different geometry, you will have different crystal scale splitting value. That means different energy gap and hence the change in color. Okay. So
Excuse
now,
me, ma'am.
yeah.
Ma'am, do we consider the effect of solvent here? Carbon disulfide.
Here for both the cases, like for the preparation of NiBr2 PPS3 whole 2, CH2 is used as a solvent. In the second case, like when we are getting this cream colored complex, we are not doing anything. Like if the complex was synthesized at minus 78 degrees Celsius and when it is heating, like it is warming up to the room temperature, it is going to 25 degrees Celsius, then this change in color is taking place. So there is like same solvent only, no other factors in this case. Okay, clear?
Yes, ma'am.
Okay. So now moving on to this question. Uh, Question number 26. This also came in GATE 2021 chemistry paper. Okay, so here the question is the geometry and the number of unpaired electrons in tetrakis 1 non-boronyl CO complex. This is the complex. Okay, so what we are asked is what is the geometry of this complex and total number of unpaired electrons. Fine. So, as in the previous case, we know that here the metal is coordinated to how many ligands?
Oh,
So, possible geometries are
Tetrahedral and square
tetrahedral and
planar.
square planar.
okay. So, in this case also, it is same like as there I have seen. Just wait. dz square dx square minus y square and here dxy dyz
Divided.
dxz. Okay. And here in square planar, anyone? So
Dx
what
square
DXY.
y
basically
square.
happens? What?
DXY.
Yeah. So dxy won't be here. In this case, dxy is this.
DY.
Okay. This is dxy. This is
Hmm?
dyz and dxz.
Direct.
And here it will be
DX
dz
minus y square.
square. No. This is dz square and this is dx square
No.
minus
Minus
y
y
square.
square.
So what happens in square planar is basically a square planar complex is like this. Okay. Here, no ligand is present in this point. That's why what is happening is dz squared is going that much down in energy. Okay. That's what happens in a, wait, someone is trying to attend. So that's why this energy splitting in this case. Okay. So first of all, we can understand one thing that for getting a square planar complex, our compound should be planar, right? Square planar means there will be no no ligand present in this z-axis. If we consider this as the z-axis, all the ligands are present in xy plane, right? So now, can you guys tell me that this non-boronyl, this ligand, is it a bulky ligand or it is a very small ligand,
Bulky ligand.
right? So will it be possible for it to come in same plane, all the four ligands?
No.
So you know, then what is the geometry of this complex?
Tetrahedral.
Tetrahedral.
Okay, so tetrahedral is the geometry for this complex. Now, what is the next part of the question? what are the total number of unpaired electrons. Fine. So yeah, this is the structure of this complex. You can see that this is not a planar molecule. Fine. So here also tell me what is the oxidation number of cobalt. Okay. Cobalt is a 3d7 4s2 complex, free cobalt. And in this case, this ligand means here, see how you will find the oxidation state for this. So this ligand is kind of new for us. This is not a very common ligand, right? But uh, how we can find out that what is the charge this ligand is carrying is, see, only one carbon is attached to this cobalt, right? So generally, like we can find out like that. If like in the case of Me, if Me is attached to a metal, then it gives a charge of -1, right? Whereas if something is attached to, like, how to say, this number of carbon centers can determine that factor. So here also we can see that only one carbon here it is attached, and this carries a charge of -1. So that in that way, what will happen is X plus 4 into -1 is equal to 0, or x minus 4 0, and x is equal to plus 4. So here cobalt is present in plus 4 oxidation state. Now plus 4 oxidation state means what? From D7H2 it is going to 4 electrons will be gone, so it will be a D5 complex. Fine.
Is it applicable for all bulky ligands?
What?
Is it applicable for all bulky ligands? We can consider charge of -1.
No. It's not like that. It is attached to one carbon center. That's why I said you can compare this with Me, like methyl attached to this or ethyl attached to this. All these gives the charge of -1, right?
Then
That's
other
what I
than
am saying. It has nothing to do with bulky ligand. The bulky ligand factor is just giving us the geometry.
suppose if nitrogen was attached, then
See, nitrogen, if it is nitrogen, then nitrogen carries a lone pair. So what happens is it will be a neutral ligand because it is donating the lone pair present on that. So in that case, it will carry a charge of 0. Okay. Yeah. So now then cobalt, this is a D5 complex, fine. This is a D5 tetrahedral complex. So what D5 tetrahedral complex means this? There are two possibilities. One is high spin complex and another is low spin complex. Do you guys know what is high spin and low spin complexes?
Number of paired and unpaired electrons. Like in low spin, there are paired electrons, and in high spin, there are unpaired electrons.
Yeah. Okay. So what happens is, in this case, if we fill D5 here, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So generally, what happens is, in case of tetrahedral complexes, this pairing energy, see, for pairing up, we have to, uh, that pairing energy is required. Okay, so what happens is that for tetrahedral complexes, the pairing energy is more. So generally, we can say that mostly for all tetrahedral complexes, we get a high spin complex only. But this is a special example. That's why you people should remember this. This is a special example in which we are getting a low spin complex instead of the geometry being tetrahedral. Hello. So that one of the reason for this may be because of like here cobalt is present in plus 4 oxidation state, and we know one thing that complex metals in higher oxidation state prefer low spin complexes than high spin complexes. Okay. So in this case, what is happening is we are getting a low spin tetrahedral complex. So the geometry of the complex is tetrahedral and number of unpaired electrons we can see here is 1. So the answer to this question will be tetrahedral and 1. Option number A is the correct answer. Any questions?
And please repeat why low spin complex.
Oh, yeah, just wait. Okay. See, metals in their higher oxidation states prefer low spin state than like see. This high spin and low spin, this depends on a few factors. So one among them is oxidation state of the metal. So if metal is present in high oxidation state, then they generally prefer low spin complexes. They prefer forming a low spin complex. Whereas if a metal is in low oxidation state, then they prefer high spin complex. Okay, this thing you is like applicable for all the octahedral complexes. For tetrahedral complexes, what happens is mostly we see high spin complex only. That why we mostly see high spin complexes in case of tetrahedral, it is because of the high pairing energy which is required for making a low spin complex. But this example of this tetrakis non-Bourneil complex, this is you can say one among the rare examples in which we can see a low spin tetrahedral complex. Okay, so this came also in a research paper where they studied about this, and this is one such rare example. So you guys should keep it in mind. But for your knowledge, I would like to say that mostly for tetrahedral complexes, we get high spin complexes only.
Ma'am.
Okay, clear?
Yes, ma'am.
Yes, ma'am.
Okay. Then moving on to the next question.
Yes, ma'am.
So in this question, So in this question, they are asking about the Lewis acid strength. Okay, the correct order of Lewis acid strength of BF2Cl, BFClBr, BF2Br, and BFBr2 is what? So we have to write the order of the Lewis acid strength of the given complexes. Okay. So first of all, what is the Lewis acid?
Electron pair acceptor.
Yeah. And tendency like a compound which will have more tendency of accepting an electron pair will be a beta Lewis acid, right? So if we take this example, BF3. So what happens is this is a Lewis acid. Why this is a Lewis acid? Because boron is having empty orbital.
It's that.
Yeah, it is an empty or it is having an empty orbital, and therefore it can accept electron pair. But there is one more factor which we should take into account, that is back bonding. By back bonding, by back bonding we mean that see all the fluorine atoms they have lone pairs. Okay, so what they do is from their sorry from their filled orbital they can donate the electron to the empty orbital which is present on boron. Okay, so as a result, what will happen? Anyone?
So ability to accept the electron will decrease.
Yeah. So yeah, the tendency to accept electron will decrease. Okay, so it will become, you can say more electron rich, and that's why the tendency to accept electron will decrease. So more is the back, we can say that back bonding and this Lewis acid strength has an inverse relationship. More is the back bonding, lower will be the Lewis acid strength, right?
Yes, ma'am.
Okay. So now for this back bonding, what we are seeing here is that fluorine is donating its electron to boron. So if both these atoms are having a comparable size, then this back bonding will be better than if we have a larger atom. Let's say we are having Br. So in that case, the size difference is too much. So the donation of electrons from bromine to boron will not be that much effective as it is in case of boron and fluorine. Okay. So back bonding strength. This is the order of back bonding strength. Back bonding strength. So in this case, boron is having a 2p orbital. So 2p back bonding will be better than 2p 3p. That will be better than 2p 4p. Okay. So these are the complexes which are given. First is BClF2. So in this case, this is 2p, 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 but fluorine is 3p, right? So here what will happen is this 2p back bonding will be good, will be better than this 3p back bonding, right? Now moving on to the next case, here the structure is BF2Br. So here boron is having 2p orbital, fluorine is 2p and bromine is having, anyone? Hello?
Oh, sorry.
Yeah, it's 4p. Okay. So in this case, what is happening is the back donation from fluorine will be very nice, whereas for bromine it will be not that effective. Now coming on to the case of BF Br2, this is this one, and we have another BF Br. So here again 2p, 2p, 4p, 4p. So what is happening? This have very nice back bonding, whereas for these two it will be not that good. And in this case 2p, 3p and 4p. So this not that effective. Now can you guys tell me the order of back bonding? Anyone?
The greatest back bonding would be in the BF2Cl.
Yeah. So the greatest back bonding will be in BF2Cl. Then
The least back
F2.
bonding will be in BFClBr.
no, it will be BF2Br.
BF2BR,
BF2BR,
Yeah.
then BF2.
BFCLBR, and then last
Yeah.
में BFBR2,
BFClBr. And the last one will be
BFBR2.
BFBr2. Okay. So since back bonding and Lewis acid strength are having an inverse relation, the order for increasing Lewis acid strength will be just the opposite of this, right?
Yes, ma'am.
Yes, ma'am.
So that means, yeah, here we should have written, I will write, just wait, BF2Cl, then what was it? BF2Br, BFCl, Br, and BFBr2. So here the order will be BFBr2 greater than BFClBr greater than BF2 to Br greater than Bf to Cl. So which option is the correct one? Bf. Here we can see that in option number B it is no, not option number. Yeah, option number B only. Bf Br2, BfCl Br, Bf2 Br, and Bf2 Cl. Right.
Yes,
So,
ma'am.
so option number B is our answer. Any doubt in this question?
No, ma'am.
No, ma'am.
Okay. So clear?
Yes, ma'am.
Yeah? Hello?
It's clear, ma'am.
Oh. So now moving on to the next question. So this is question number 21. The question is the MOMO bond order in eta 5 C5H5 MO CO whole 2 whole of 2 which obeys 18 electron rule is what? So in this question what we are asked is what is the bond order of this molybdenum, right? So what is 18 electron rule?
The compound, if it has in total like 18 electrons, so it is said to be the most stable compound, and we see if it follows the 18 electron, we actually count
Yes.
the valence electrons.
So now you guys can calculate the total number of valence electrons for this complex.
Yes, ma'am.
Yeah, count. Molybdenum is having how many electrons?
6.
Six
Yes.
electrons.
Yeah.
No.
Four. Four.
Yeah. Okay. Everyone got this answer?
Okay.
Yes, ma'am.
Yes, ma'am.
Okay. So we are having total 30 number of valence electrons for this complex. This is the structure of this complex. MO, CO, CO. Okay, so one more is attached. We don't know whether like this is bridged or what. So what happens is for 18 electron rule, the total number of valence electrons should be how much?
18.
No, no. You have to consider this. Now, there in this complex there are total how many number of molybdenum?
2.
Then what should be the total number of electrons for following 18 electron rule for the whole complex?
36.
36
Right.
electrons.
Yes, ma'am.
So
26.
here how many less electrons are there?
6.
6.
6 electron.
Okay, so 6 electrons are less for fulfilling this 18 electron rule. Now we all know that in a bond there are total how many number of electrons in one bond?
2 electron.
2 electrons.
So that means 6 by 2. So we need 3 more bonds for fulfilling 18 electrons,
Yes, ma'am.
Yes, ma'am.
right? So now we know that between two molybdenum there are 3 bonds. So the answer to this question is
3.
so the molybdenum bond order in eta 5 C5H5 MoCO whole 2 which obeys 18 electron rule is 3. Clear?
Yes, ma'am.
Yes, ma'am.
Yes.
Yes, ma'am.
So the next question number 8. So the question is reaction of lithium aluminium hydride with one equivalent of Me3N HCl gives a tetrahedral compound which reacts with another equivalent of NMe3HCl to give compound N. The compound N and its geometry respectively are. So here we have to say what is forming and what is the geometry of that complex. So first of all, this reaction is happening is LiAlH4 4 plus NMe3HCl. So at first, whatever is forming, let's say that's compound A, it is having a tetrahedral geometry. It is given in the question, right? See, gives a tetrahedral compound. Then what is happening is to this compound A, we are again adding another equivalent of NMe3HCl. So this is giving compound N, which is we have to write the geometry for this complex, right? So what happens in this type of cases is wait, if we consider BH3 NME2 type of complex, what happens in those cases is three. Okay, so adduct type of thing like adduct formation will take place in this case. So in this case also, what will happen is this NME3 will form an adduct with AlH3. Okay, so this will form in the first step. You know why this adduct formation is taking place? This is because this nitrogen is having a lone pair and aluminium being same as boron. So aluminium is also having empty orbital. Boron and aluminium shows like they belong to the same group and they show similar type of properties only. So aluminium having vacant orbital and nitrogen having lone pair in this kind of reaction, what happens is adduct formation take place. So this nitrogen is donating its electron to aluminium. So this is what it forms, right? So this is compound A and this is having a tetrahedral geometry. Now what will happen if we add another equivalent of NMe3HCl? NMe3. So see, here we can see that we know that what is forming. Okay, in first here, nothing is given. So first of all, this will be NH4. Now two molecules of NMe3 will coordinate with AlH3. Okay, that's what will happen. AlH3 and there will be two molecules of NMe3. So on adding another equivalent of NMe3, what is happening is we will get this complex AlS3 with two molecules of NMe3. So AlS3 with two molecules of NMe3 only in option number C and D we can see that as an option. Okay. So now what is the geometry of this complex? So earlier it was given that for compound A the geometry was tetrahedral. On adding one more ligand, on adding one more electron, what is the higher symmetry? It goes trigonal bipyramidal. Pentagonal is what? Pentagonal we say if we have a planar molecule like this, right? This will be a pentagonal. This is a pentagonal shape. But in this case, what we will get is trigonal, sorry, is trigonal bipyramidal, means this Al will be here with 3H and 2 NMe3 will give their lone electrons. So in this case, the answer will be trigonal bipyramidal. So the answer is the compound which will form on reacting LiAlH4 and 2 equivalent of NMe3 HCl will give AlH3 NMe2 NMe3 whole 2. We will get this, and the geometry of this compound will be TBP, that is trigonal bipyramidal. Okay, hello.
And reason for TBP geometry is
The reason for see, we know this thing. Wait, see, for having one electron, sorry, one bond pair, what we have is the geometry is linear. For having three bond pairs, we will have a geometry of trigonal planar. For having two bond pairs and one lone pair, we have geometry of trigonal planar, but the shape is bent. For having four, uh, four bond pairs, the geometry will be tetrahedral. Whereas for having five bond pairs and zero number of lone pairs, we see a trigonal bipyramidal geometry. Okay. So how can I say? You guys know that VSTPI chart, right? I have maybe I can share that with you. Can you guys see this? I don't know. Wait. Is this visible? I don't think. Is it visible? No, no.
No, ma'am.
Just wait. So this one is what I was trying to show. You guys can see.
Yes, ma'am. Yes, ma'am.
Okay. So in this case, we can see that we know, right, that there are five bond pairs and no lone pair for this complex. So the geometry will be trigonal bipyramidal as well as the shape will be trigonal bipyramidal. You guys can take a screenshot of this or anything. It will be helpful for knowing the geometry and shape of different main group compounds. Fine.
Yes, ma'am.
Ma'am, when the shape will be pentagonal?
What?
When the shape will be pentagonal?
See, in this case, sp3d3, you can see PVP means pentagonal bipyramidal. And the shape will be like this arrow means same shape. Okay. So, and the shape will be also pentagonal bipyramidal. Okay. So for sp3d3, that means when we are having seven number of bond pair and zero number of lone pair, then we will get the geometry of the compound as pentagonal bipyramidal. The shape will also be pentagonal bipyramidal only. Fine. Hello.
Ma'am, I'm asking for option number D, where the shape is given pentagonal.
Okay, you are asking for. Okay. So what will would have happened? Suppose in this case, like this means pentagonal bipyramidal, na? Wait, I will draw. When there will be two number of lone pair and five number of bond pairs, in that case, we will get pentagonal shape. You understood? But see,
Wait
pentagonal
once.
bipyramidal. Yeah, just wait. See. This means pentagonal bipyramidal, right? So this we are getting when number of bond pairs are 7 and number of lone pairs are 0. So when there will be no electron, sorry, no ligand in these two places, that's what we can say that we are having two lone pair and bond pair 5. In that case, we will get a pentagonal shape. Pentagonal, yeah, pentagonal shape we will get, but the geometry will be pentagonal bipyramidal only.
Okay, ma'am.
Okay.
Excuse me, ma'am.
Yeah.
Ma'am, here can we say that the complex are changing from tetrahedral to we are defining that whether it will go from to trigonal bipyramidal or pentagonal. So if we transfer tetrahedral to trigonal by trigonal pyramidal, then the geometry changing from no, non-planar to non-planar. But the tetrahedral is not in a planar, so the energy difference is very high for if it will be go from tetrahedral to pentagonal. Am I right, ma'am?
Yes,
So
you are
it is
absolutely
not
right.
going like
Yeah,
that.
we can explain in that way as well. Yeah. So yeah, when we can going from tetrahedral to trigonal bipyramidal is easy. Like just one ligand is adding. But for going from tetrahedral to pentagonal means all the ligands have to come in same plane, and that is difficult. So yeah, that is a correct way of explanation. Yeah. What is your name?
Ma'am, Ravindra.
Yeah, you are absolutely correct.
Yes, ma'am.
Fine. So, any doubts from today's class? Last time, is Aarti there in class today? Okay. Aarti, there is a chat. Somebody asked, in case CO metal replaces the anion, which type of complex is formed, ma'am? This is for which question? Sai, are you there? Yeah, I think Sai is not there. Yeah, okay, you are there. So you were asking about which question? This one? Okay, so this thing completely, like, see, if it is cobalt, then we have to check for everything. Like, what is the electron configuration for that? Like, for cobalt, what will happen? Cobalt is having how many electrons? Tell me. It will be better if you talk, or else I have to go. Hello? You're talking about this question only, right?
No, ma'am. Third question.
Third question, okay. In this question, where is cobalt? Okay, in this one. But I think you asked what will happen in case CO metal replaces the Ni. So CO is replacing Ni. Then that is the first question, right? Your side. Hello.
Yes, ma'am.
Yeah. Tell me your question. You're talking about this one or the NiBr2 PPS3 whole to one?
This one.
Huh?
Ma'am, this one first.
What will happen if nickel is there instead of cobalt?
Ma'am.
So here, okay, for the same complex. First of all, for the same complex, this thing will be different, right? For nickel, it will be D8H2 nickel in plus 4 oxidation state then. Nickel, if we consider this as nickel, then it will be nickel plus 4 oxidation state, and it will be D6, D6 complex, right? So D6 complex means, first of all, this will be tetrahedral only. I don't know any complex like that, compound like that exists also or not. But D6 means for high spin, you will see 1, 2, 3. For high spin 1, 2, 3, 4, 5, 6. And for low spin 1, 2, 3, 4, 5, 6, 5, 5, 6. Okay, so you are saying what will happen in this case? It will be high spin or low spin? Huh? Yeah?
High
Hello?
spin complex.
Yes. So it will be a high spin complex only. So what I said is this is a rare example in which this is happening. I will see if any compound like this even exists or not, and I can get back to you. But as I think it will be a high spin complex only because the pairing energy here required is too much.
Ma'am, I was asking now that cobalt is attached to carbon. And I was asking that if nitrogen was attached, then you said that cobalt will carry
Okay,
zero
you are
charge.
saying nitrogen, but that is written Ni. That's why I got confused. Okay. You were asking what will happen if it is nitrogen instead of that carbon.
Yes, ma'am.
Okay, okay. So then it will be zero here.
And
Okay.
ma'am, in case of
And
phosphorus,
then oxidation state will also not be high and we will get a high spin complex for sure if it is nitrogen. Okay.
if it will be phosphorus, then
If it is phosphorus, then also if phosphorus is also having lone pairs, so it will also be a neutral ligand. Okay.
okay.
Yeah. It will be also, see, we judge on basis of that only. If like for all these halides, they are -1 charge, they carry a charge of -1. But this NH3, water, or anything which is having a lone pair, even if we are having an alkene, let's say we have an alkene or an alkyne, anything like that will be neutral charge ligand. Okay.
Okay, ma'am.
Yeah. So if you guys have any question, any doubt, you can mail me in this mail ID, which I'm writing in the chat box. Okay. And that's all for today's class. Anybody is having any doubt?
Ma'am, it was a nice session. 5 questions completed.
Yeah, thank you. So, almost 2021 questions are over. So, from next session, we will start 2020 questions. Okay. Yeah. So, you guys can once go through that. It will be helpful for you and me both. Okay. Thank you.
Thank you, ma'am.
Yeah. Thank you.